Welcome back my dear friends. A very good morning, good afternoon, good evening to all of you wherever you are in this part of the globe. And this is the DADM 3, which is Data Analysis and Decision Making 3 course under NPTEL MOOC series. And this total course duration is spread over 12 weeks, which is 30 contact hours, which when converted into number of lectures is 60 in number, considering each lecture is for half an hour. And each week you have 5 lectures totaling to each being of half an hour. So, you have 2.5 hours of lectures in a week, and after each week you have one assignment. So, if you see, this is the 45th lecture, which is the last lecture for the 9th week. We have already taken 8 assignments. After the 9th week ends, you will take the 9th assignments, and in totality you will basically be taking 12 assignments, and after which you will basically be appearing for the final examination. So, of the other topics of multi-objective programming, the concept of optimization, goal programming, I was basically going through the problems. So, in this 45th week, which is the last lecture in the 9th week, I will discuss further the analysis of the results, and rather than going to the details solution techniques, I will come to that later. Now, if you consider the problem which we were discussing, where it was trying to, and that quadratic programming concept, which was first part was half x, I am not talking about the transpose, it is x into q into x, which is exactly the same thing as you did for finding out the variance covariance metric multiplied by the square of the weights, and the other part was c into x, which was basically summation of wi's into ri bar. So, here x are the decision variables which are wi's, and c returns which are considering. So, if we consider in the portfolio return corresponding to portfolio transaction cost, that means each transaction of buying and selling basically entails some cost of w plus and w minus, even though both the values are outflows from your pocket, but I am just denoting as w plus and w minus with the suffix I corresponding to the ith stock. So, if I consider the transaction cost for the portfolio returns versus the portfolio risk, I would basically have a graph accordingly like this. So, these maximum values are towards the x axis, which is very difficult to differentiate here. Next, we will consider an outline of the portfolio maximization of return and minimization of risk. Now, there you can basically combine them using the concept of convex combination function. Now, it could have been like lambda weight between 0 and 1, lambda into returns plus 1 minus lambda into the risk. So, considering that you are putting weightages. Also, it can be the case where the lambda and 1 minus lambda or lambda 1 lambda 2 can be higher values of higher positive values depending on the total concept of weights or importance you are going to place on those metric, whether returns or risk, that is a different question. So, here you have maximization of the returns by and also minimizing of the risk. Now, this part is actually the way how you are going to formulate the quadratic programming, but remember there is a difference here. So, I could have minimized the actual portfolio variance. In that case it would have been suffix p without the star. The star means that I am predefining some value over and which the portfolio risk should not be, that means it has to be less than that, or you want to basically bring down the concept of the risk. So, this is something to do with those safety first principle which we have considered in the utility concept, where trying to basically shift the mean depending if there is a distribution which is a normal one, depending on maximization minimization, we may try to shift the whole distribution mean values either to the right or the left considering the number line, or else we can shift or try to basically increase or decrease the value of r suffix l or r suffix f, f is the risk free interest rate. And maximization of rather than RP star, we could have basically maximized RP, which was technically the summation of Wi into Ri bar. Similarly, as I just mentioned, sigma square p without the suffix actually is basically a double summation Wi into Wj sigma ij, where sigma ij is the covariance values. Now, what are the constraints? The constraints are in this simple case that if I have the returns, so if the returns are increasing, there would be some increase and decrease. So, returns can be either positive or negative, but we will consider that in the long run the combined returns of the portfolio values would be greater than what we have actually started with. So, some of the values here, these RIs can be negative also. The second one is that portfolio returns now actually, which is what I just discussed. So, this value, the value here actually could have gone here, and the value here could have gone here. That means, I replaced the actual value with a such with a fixed value, which I am going to increase for the case of the returns and trying to decrease for the case of the risks. So, these are the values which are being transformed. So, this has gone here and this has gone here. So, we will ensure in this case the yellow highlighted ones means the portfolio actual returns is greater than RP star, as it should be, because I want to ensure the return of the portfolio is over a fixed value, which may be market dependent, may be depending on my uncertainty, may be depending on my concept of utility, whatever it is. Me means I am the investor. Similar in the case, the risk would be the whole risk of the portfolio, that is double summation Wi into Wj into sigma I sigma j into rho ij or sigma ij would be basically the portfolio risk, which has to be less than equal to sigma square star suffix p, which is again a predefined value by the investor or as per the concept of the utility. And obviously, the summation of the weights are equal to 1, and each of the weights Wi's are between Wi minimum and Wi maximum. So, if I basically plot the return and the risk, so the return and risk of the as it should be. So, this basically mimics. So, there are obviously some simulation values which are not matching it, but in generally if we see the trend, so these values are exactly what we are basically getting. So, this is the risk return profile, risk along the x axis and return along the y axis. So, if I basically want to find out any particular portfolio, their corresponding weights and returns, I basically find out these are the weights. Here W is a vector. Similarly, for other case of risk and return, I would have some other weights corresponding to the third value, I would have other weight. So, these are the different combinations which I have. So, if I want to know the weights, obviously I will plot the minimum threshold value which I have RP star, and then the weights are plotted along the y axis. So, these at any value, the threshold value, say for example, threshold value is 9 into 10 to the power minus 4. So, at this instant there are only one stock, the dark blue one, light blue one and the green one. If I consider any value here, so here there are different colors combinations, it is very difficult to see, I understand. So, here are the different color combinations. So, there are much more number of stocks which are basically being utilized to formulate that portfolio, which is the optimum one. Then if I basically have the concept of the threshold of the portfolios, threshold value remember, and the portfolio risk, which is the Pareto plot, and this I am doing for the Hong Kong Stock Exchange. So, the Pareto plot as it should be, this is the value. So, here any combinations would give me, I am that level of utility for any combinations along that line gives me the same level of satisfaction. The next value which I considered is basically the maximization of the return or threshold value of the return and minimization of the risk. Now, see here again the interesting part, this is exactly what we had seen earlier. So, this is the quadratic one. So, you have half C Q and N into C, which is basically C square. C square is basically the weights which are the one values which are here, and Q is basically the variance covariance matrix. And I want to basically find out this is the minimization. Obviously, risk has to be minimized, and maximization would be corresponding to the threshold value. That means there is a certain value over and which the portfolio return should be. So, the threshold value is RP star, which is fixed by the investor depending on his or her utility and the market risk or the perception of own individual risk. And the return on the portfolio is given by the summation of RIs into WIs. RIs are again RIs or RI bars depending on how you have been able to formulate the problem, and WIs are the weights corresponding to the each and every scripts you want to find out. So, again the constraints remain the same. I am trying to keep the constraint as simple as possible. You can make it more complex, more practically oriented, but these answers are quite well and enough, give there a lot of information that how you basically should formulate your portfolio. So, in the first case again you are the first constraint basically means that there would be some RIs which are positives, there would be some RIs which would be negative, but you will basically formulate that in such a way that 1 plus RI multiplied by the weights which you have should be greater than the value of 1. 1 means basically the returns which you are ensuring as when you start at a value of 100 or 1 or 2000, whatever it is, that value has to be greater than 2000 or 100, whatever. And again you need to ensure that the returns of the you are trying to maximize the difference. So, obviously, the returns of the portfolio should be greater than RP star value as it should be, and the sum of the weights are 1 actually as it is, and the weights are always bounded between WI min and WI max for each and every I value, I being 1 to capital N. Then if I am doing it for the DAX, if I basically plot the risk return profile, risk being along the x axis, return being along the y axis, I have the graph as it is given. So, these are the graphs, and these are the simulation values. They are coming out to be quite nice with respect to the actual theoretical values. So, theoretical values are this. So, I am just drawing them apart in order to make you understand how the shape would look like. See here again a risk and return profile, then again a risk return profile value, then again a risk return profile value would give me different weights. In the similar way, when I find it out, a risk return profile gives me W1 means for that particular instant. Then again if I basically plot it, I get another W value. These are vectors, remember. So, similarly, I keep changing the threshold values and I basically can simulate such hundreds of points in order to basically find out how the graph will proceed. Then again when I depending on the number of simulation runs which I do, I plot the values of the weights along the y axis and the minimum threshold of portfolio returns, which is for the DAX case the x axis. Now, here you will see that I am basically changing the different indices in order to make you understand that for the same type of equations they would give you very similar type of interesting results for different type of stocks, which means that the models which you are trying to utilize are quite efficient enough, decently efficient enough to give you interesting results. So, you may find out that as for higher values of threshold, say for example, only one stock dominates, others are gone, but if you basically go for lower values, you see there is a huge amount of variations in the weights of the total portfolio. So, that means there are different types of scripts. Again when I do it for the DAX, trying to basically formulate the Pareto optimality frontier for the portfolio risk with the value of the portfolio returns. Returns means over the threshold value. This so again I get this Pareto optimal front So, these values so they will give me the of the Pareto optimal fund that the level of satisfaction would be same for all the points, but the how you are able to combine the different weights would is basically what is the question. Now, we will just consider another simple formulation. I will come to the RRPO formulation later on for the chance constraint problem nomenclature, that is what we will do when we consider goal programming. So, just to give you the idea, so you have the returns of the jth stock, again j is equal to 1 to capital N for the ith day. So, technically in when you are trying to basically formulate with respect to the time should be 1 nomenclatured by t, but we have taken here as I. Here R by Gi basically on the nominal value of the lost return of the jth stock at the ith day. So, we will basically try to find out the average. Sigma x and xj's are the corresponding vector of variance of the stocks and the weight of the investment for the jth stock, which is of interest to us. N is the number, capital N is the number of stocks considered in the portfolio. T is the total time period, like 240 days, 1 year, or 480 days, 2 years. These values of alpha and beta, which is very interesting, is basically there would be two levels of risk. One is what the investor is perceiving from his or her side, and there is a market risk. So, it may be possible that I think the market is very risky, but actually it is not. So, my perception of value of alpha based on which I am trying to basically formulate the problem and the value of the market risk in reality, which is beta, may be different. So, alpha can be greater than beta, alpha can be less than beta, the values of alpha beta if they are very close to each other, that means I am able to formulate my problem with a set of information which I have from my side basically mimics or tries to basically be as close as possible to reality and find out the concept of market risk. So, here I am denoting alpha as some level of confidence for var. What is var? I will come to that later, and beta is basically the value of given probabilities corresponding to constraints 1 and 2. So, obviously, there would be some constraints which would basically imply that what is the level of such risk or level of confidence I am going to put onto these constraints depending on the market values of market values fluctuations of the actual information set or the data set. Why? Because the prices of the stocks are fluctuating. So, if they are fluctuating, it would have an effect on the returns, which is R, and if the returns are fluctuating, obviously there would be some probability based on which, not the probability distribution I am talking about, there would be some reliability value or robust value between which the value of the stock prices will fluctuate. And lambda 1, lambda 2 are the variables which basically ensures a convex combination you are going to put for the risk and return, and gamma is the variability over which the minimization of the C var would be done. So, alpha is basically for the var and gamma is basically for the value of C var. So, value at risk var or conditional value at risk C var are the concept which are used in finance to basically find out the overall risk of the portfolio. As we have standard deviation, as we have beta, not this beta, what is shown here, beta as we see in the concept of capital asset pricing model. So, these values of as I was talking about, this conditional value at risk and value at risk are the risk concept which are used in portfolio. As you have, as I just mentioned, standard deviation also, variance also. But remember, there are some very unique properties of conditional value at risk or C var, and it has an advantage of the value at risk. This is just I am mentioning for your own information. The other nomenclature or other symbols which are important for us is the conditional value at risk for the portfolio based on the loss. Delta L is basically the loss. I am only considering the loss, it could have been basically for the profit also, but in that case risk would be given a different picture based on which I will try to find out that how good or bad my total portfolio is doing, considering I am looking at the positive side. Here in this case I am trying to find out the conditional value at risk of the distribution which is pertaining to the loss distributions only. RPL is basically value of the portfolio return considering a loss distribution that needs to be maximized. Delta L is the loss function, and the values which is given from 14th to the 18th one are certain to do with a type of problem formulation which we will see later, and and it is 14th to 19th, and do not confuse the variable wj as the weights one. It is basically a dummy variable which will be utilized to formulate the problem in the robust formulation being important for us. So, what we do is that use the concept of minimization of CVAR or conditional value at risk, and also we try to basically find out the maximization of the return on the portfolio. So, minimization of the minus value basically means the maximization. So, the first part which we have is the conditional value at risk which needs to be brought down. The second part with the minus sign, minimization of minus is basically increasing the return on the portfolio, and very simply the constraints have been formulated in a very simple manner. In the first case I am ensuring in the probabilistic case. So, obviously it need not be probabilistic, it can be in the simple deterministic also. In the probabilistic case, it is the probability of the actual formulation of the portfolio's conditional value at risk is always less than the conditional value of risk which we are proposing based on our level of risk. So, that should be in the probabilistic case, that if that value is less always, then obviously we are 100% sure, but if it is not less than CVAR always. So, there would be a level of reliability that is given by beta 1. And in the second constraint, you have basically the probability of the return of the portfolio is greater than the return which is stipulated, which is RP del L corresponding to the loss distribution, and that the level of confidence is basically beta 2 depending on how reliable the results are. And obviously, it means the sum of the weights of the portfolio of the scripts are greater than 1, and the sum of the convex combination of the weights lambda 1 lambda 2 obviously should be 1. So, here the values which means the uncertain parameters and the chance constraints are highlighted. So, the uncertain parameters, chance constraints would be corresponding to the constraints, the probabilistic sense, and the uncertain parameters actually are the returns only, because based on the prices you have the returns being probabilistic, you will basically have different type of average returns, different standard deviations, so on and so forth. So, they will keep changing. So, actually information based on the prices would basically dictate how the formulation and the values have been obtained. So, again the chance constraints are given, I will just highlight it. And the uncertain parameters I have already discussed are basically the R values. So, these are the returns of the scripts. So, the data we are going to take is taken from the for 12 different countries, which is the Australian exchange, Brazilian, France, DAX for Germany, FTSE for England, Canada, Hang Seng is for Hong Kong, Argentina, Nikkei for Japan, NSE, not the BSE, NSE for India, New York Stock Exchange for USA and for Singapore. The data for each of the index in value, that means not individual, but for the index, which basically mimics the market to the best possible extent, is considered for a range of 10 years from 2000 to 2010, all the 10 years, and this corresponds to a total of about 2800 readings, which is 2840 trading days. We divide the data into two categories. So, this is important to note that the reason why we divide the data into two regions is basically we want to basically have an in sample and out sample. In sample is where we have the model, test it, find out its efficacy, and then basically retest the model for a data set which is totally new, such that we want to find out how good or bad our model is or how robust our model is. We will use the formula of the return. So, this capital R and small r are immaterial here. So, we will use the return of the stock is given by ln of P2 by P1, that is price of day 2 divided by day 1. To obtain the return value series, where P indicates the closing index price. So, you will be taking the prices at the end of each day, while the suffix T specifies the day on which the price is reported. The descriptive statistics like the mean, standard deviation, skewness, kurtosis, minimum, maximum, the daily returns of all these 12 scripts are given here. So, on the first column we have all the scripts, and the second till the last one are basically the mean values, the median, the standard deviation, the kurtosis, skewness, minimum value and the maximum value. So, you can basically utilize the data accordingly and then decide that whether it should be basically negative distribution, the loss distribution or the positive distribution for the returns. Now, we did consider this concept of extreme value distribution in DADM 1. So, you will basically in a very simple manner. So, EVDs or extreme value distributions plots for all the 12 indices are plotted using the bootstrapped estimates. That means, you find out the estimates for the shifting window depending on how you have been able to formulate, and then bootstrap it to basically have a whole set of data runs. And for the positives, we will only give the EVD runs for the DAX only. So, this is basically left skewed or right skewed depending on whether you are going to consider the positive or the negative returns of the stocks. So, you will basically have different type of left and right skewed for all the 12 indices, and if you see the DAX mu values are given minus 0.028, I am only reading the values, and the DAX sigma values is 0.01. These are the theoretical extreme value distributions considering the QQ plots, which is an important factor we have also considered in some, not in details, but we have mentioned that in DADM 1, where we consider that given any the theoretical standard normal distribution is basically compared with the empirical distribution of the minima, similarly for the maxima, and we do maximum minimum being for the case for the negative returns and the positive returns. Similarly, we do the theoretical extreme distribution values on the x axis and try to basically find out the simple returns and the distribution of the minimum or the maximum in order to find out how they match. So, obviously, if it is a straight line, it means that the QQ plots are fitted the best, based on which we will consider that empirical values of the distribution for our case of understanding and consider those values for our general runs. With this, I will end the 9th week and consider more about this goal programming and other concept later in the starting from the 10th week. Have a nice day and thank you very much.